Hey guys, welcome to the Pre-Calc Unit 8A review video. The first group of questions we are going to simplify and then rewrite in exponential form or radical form. Question number 1, I want to evaluate 32 to the 1/3 to the negative 3/5. First thing I'll do is apply my power to a power rule by multiplying those exponents. And if you notice, you've got 3 in the denominator here and a 3 in the numerator there. So that ends up giving me 32 to the negative 1/5 power. The negative exponent is going to take the reciprocal of your base, so it's 1 over, and then 1/5 is the 5th root. So 1 over the 5th root of 32 is equal to 1/2. Next question, simplify, leaving no negative exponents. I'm going to start here, 16 to the 3/2. At this point, I'm hoping you guys can do that without a calculator and also without rewriting this. That is going to take the square root of 16, which is 4. So 4 cubed is 64. In my denominator, I still have a 4. Now let's take care of my m's. M cubed over m to the 5th. 3 of these will cancel with 3 of those. I'm left with an m squared in the denominator. Now the way I'd handle this, I know you guys aren't fans of fractions, but remember the property of exponents when we divide the bases. You subtract. So this is going to be n to the 1/3 minus a negative 1/3, which will give me 2/3. So in the numerator, I have n to the 2/3. Now, I need to cancel 64 over 4. That's going to be 16. It doesn't say in radical form, but I'm going to practice that anyway. 4 goes into 64 16 times. So I have 16 in the numerator. Then I have the cube root of n squared. And in my denominator, I just have the m squared. Question number 3 is probably the most difficult question on this entire exam. There's so much going on here. So let's take a look in the numerator first. Parentheses, and I have this squared on the outside. So I have to apply this squared to everything on the inside. 3 squared is 9. X to the 1/3 squared is going to be x to the 2/3, right? You multiply those exponents. Y to the negative 1/4 squared is y to the negative 1/2. And then you have that z. My denominator, I have 72, x to the 5/3, y to the negative 3, z to the negative 1/2. Now, 9 goes into 72 8 times. I have an 8 in the denominator. What I would do here most likely is apply my rule for dividing the bases, which is subtracting those exponents. I know they're fractions, but I've got 2/3 there. I've got 5/3 there. Subtract those. Now, you can write it as a negative exponent, or you can just write it in the denominator, because notice I have more down here. 5 there, 2 up there. So 2 will cancel with 2 of those. I'm left with x to the 3/3 in the denominator, which obviously I can simplify in a second. What happens here with the y's, those negative exponents, so that will go to the numerator, that will go to the denominator. We end up with more in the numerator. 3 minus 1/2 is 2.5, which I'm going to write as 5/2. And then same thing here with the z. That comes up top, so I'd have 1 plus 1/2 is 3/2. Z to the 3/2 up top. So now all it's left to do is write this without the fractional exponents. Notice in your numerator, they both have a 2 in the denominator, so I can put those both under a square root. And that would be y to the 5th and z cubed. And then the bottom, 3 over 3 is just 1, so that's just 8x on the bottom. So a lot of work to get that, kind of challenging. All right, this one should be a little bit easier for us. I'm taking the cube root. It says write in exponential form. Notice the 27 is under the radical. So first thing I would do is take the cube root of 27, which you guys should know is 3. Then remember, my root is the denominator of my fractional exponent. So this would be the numerator, that'd be the denominator. And I'll just go through and rewrite those. So x to the 7/3, y to the negative 3/3, times. Again, the coefficient here is underneath the radical, so we need to take the cube root of 8, which is 2. And then x to the 2/3, y to the negative 6/3. Now I need to multiply those bases. So 3 times 2 is 6. When I multiply the bases, I add the exponents. So I have 7/3 plus 2/3. Now, I'm not going to write the whole thing out, but 7/3 plus 2/3 is 9/3, which is a 3, so that's x cubed. Then I have y to the negative 3/3 minus 6/3. So, I mean, you can call this a negative 1 and that a negative 2. I'm going to get negative 3. So y to the negative 3. That's an exponential form. It doesn't say don't leave any negative exponents, so I would probably leave it like this, but this is equally correct. Okay, let's talk about some graphing. Remember, when we graph an exponential function, there are 2 key points on every exponential function before you transform it. Those 2 key points are 0, 1, and 1 base. So that's how I'm going to be approaching these. In question 5, we have a transformation. There's a negative on the outside, which means a reflection in the x-axis. So instead of looking kind of like this, you're going to reflect that in the x. It's going to look like that. My base is 2. So here's how you approach it. First of all, sketch in your asymptote. Every exponential has a horizontal asymptote. Here it is. Now, instead of 0, 1, I need to reflect that in the x-axis. It'll go down here as 0, negative 1. My other key point, 1 base. So 1 base, my base is 2, would normally be here, but reflect that in the x, it goes down here. Now notice it says 3 ordered pairs. So remember, we're taking exponent, power. So 2 to the first is 2. 2 squared is 4. So my next key point would be over 2 down 4 because we are squaring our input. That's probably the easiest one to get. And now you'll neatly sketch that in and label those ordered pairs. 0, negative 1. 1, negative 2, and 2, negative 4. So this is what I expect to see on your exam. You're going to write down the transformations. You're going to show me the sketch and label 3 key points. I'm not going to take the time to do this, but it's easy to check these. Remember, that's your x, that's your y. Plug those both up here and see if that's a true statement. All right, question 6. My base is 3. This right here, a plus 1 with the x is going to be right or left, and because it's plus, that means left 1. So what I would do here is sketch your vertical, left 1, and then don't forget we have an asymptote horizontally as well. Now, my key points, 0, 1. Remember, we kind of shifted our origin to here with the transformation. So 0, 1 would be here, and 1 base, 1, 3. Now, you need to identify 3 points, all right? Those of you that have a really good understanding of these exponentials would know that this is going up 1/3 because negative 1, 3 to the negative 1 is 1/3. If that's a little bit challenging, what you could do is say, well, if I go over 2, I have to go up 9. Even though I don't see it on the graph, you can write down that coordinate, which would be 1, 9. I'd be fine with that. But if that kind of bugs you because you can't see it on the graph, then you'd have to go with this one right here, which is negative 2, 1/3. All right, so let's sketch that in. Key points here, the 2 obvious ones would be negative 1, 1 and 0, 3. Like I said, the other one's going to be 1, 9, or you'd have to get the negative 2, 1/3. And again, you can check all of those with your x and the y into this to verify that they work. All right, number 7. This one is very challenging because we've got an exponent that we need to factor out the negative. 3 minus x. We have to factor out the negative and then rewrite it as x minus 3. The reason for that is because if you don't, it's harder to determine whether you go right or left. So in this case, I've got 3 transformations. The negative up with the exponent is a reflection in the y. It's x minus 3, so it's right 3. And this minus 1 tacked on the end is down 1. Okay, so I'll shift my axes. Right 3, sketch that in. Down 1. And And then on top of that, I'm reflecting in the y-axis. So here's our normal exponential. Reflect that in the y-axis. It's going to look like this. Okay, so here we go. 0, 1. If you reflect that in the vertical, it's not going to move. So I'll make it a little bit easier. 1 base will be 1, 2. So normally, without the reflection, 1, 2 would be right here. Sorry, right here. But you have to reflect that over. And then I would have 2, 4 reflected over would be right there. Sketch that in. And just label those coordinates. All right, so what do we have? 3, 0. 2, 1. I'm kind of going backwards here. 1, 3. And again, you could check those in the original equation pretty easily. All right, our last one. We've got a negative in front. That's a reflection in the x-axis or in the horizontal. A plus 2, which means left 2. And a plus 2 on the end, which means up 2. All right, so left 2, up 2, and a reflection in the x. So again, visually, here's your exponential, but you have to reflect it in the horizontal, so it'll come down here. Instead of going 0 up 1, you go 0 down 1. Okay, so then our base is 4, right 1, down 4, 2, 3, 4. And again, we're off the graph here because if you square 4, you get 16. So I'm going to end up with a point that's way down here. You can tell me what it is. It would be 0, negative 14. Or understand my base is 4, so that would be 1/4. Down 1/4 from there. So let me sketch that in. And the coordinates here, I see negative 2, 1. I see negative 1, negative 2. And then you could have 0, 14. Or you could have negative 3. And that would be 1 and 3/4 because it's down 1/4 from here. That's probably the harder one to get, so I would stick with these 3 right here. All right, let's move on to some equation solving. Solve each equation, showing all work. So remember, the goal here is to get common bases, right? Until we review our logarithms in the next unit. If you notice, my base is 2. I need to get rid of everything else with it. So first step here would be add 7 to both sides. So 4 times 2 to the 3x minus 1 equals, what's that, 16? Now I divide by 4, so I have 2 to 3x minus 1 equals 4. Pretty easy to get these to have the same base. I need to rewrite this with a base of 2. So 4 is the same as 2 squared. So I have 2 to the 3x minus 1 equals 2 squared. Now you can set those exponents equal. So 3x minus 1 equals 2. Add 1, 3x equals 3. Divide by 3x equals 1. Very easy to check. You take that, plug it up here, and see if that gives you a 9. All right, I'm not going to take the time to do that now, but it's very easy for you to do. All right, number 10. A little complicated here because I see multiple bases. This is nice, single base. So what we need to do is apply our properties of exponents to rewrite that as a single base of 9. I'll just take 2 steps to do this. My numerator becomes 9 to the 3x plus 1, because remember, when you multiply your bases, you add your exponents, divided by 9 to the negative 5th. A couple ways you can view this. You could take this here and write it in the numerator, or just subtract. The exponent's going to be this minus negative 5. 9 to the 3x plus 1 minus a negative 5 equals 9 to the 7x plus 3. Now you just set your exponents equal. Right? Obviously, this here is going to give us 3x plus 6. So here's your equation. 3x plus 6 equals 7x plus 3. Subtract 3x from both sides, you get 4x. Subtract 3, you get 3. Divide by 4, x equals 3/4. Right, again, pretty easy to check. I'm not going to take the time to do that. 11. Little different type of equation. Here's my base, so I need to isolate that first. All right, subtract 10, that gives me 2x to the 3/4 equals 54. Divide by 2, x to the 3/4 equals 27. Now notice the difference here. Your variable is in the base. The equation's up above, your variable is in the exponent. So we approach it very differently than this. Here, I don't need to get like bases, I need to undo an exponent. Well, the way you undo an exponent is you take the reciprocal exponent. So I need to take both sides to the 4/3 power. Okay, so x equals, because you multiply those, you just get a 1. 27 to the 4/3 is the cube root of 27 to the 4th. I'm hoping you can do that without a calculator, without a lot of work. The cube root of 27 is 3. 3 to the 4th is 81. All right, number 12. Again, we're back to our variables being in the exponent. So what I need to do is get like bases with those two. It's going to be a 2. I'm going to replace the 8 with 2 cubed. And replace the 4 with 2 to the negative 2, right? Because it's a fraction there. So this will be 2 cubed to the x plus 5. This will be 2 to the negative 2 to the 2x minus 1. Now what I need to do is distribute. I'm going to multiply those exponents. Don't forget to distribute. 2 to the 3x plus 15 equals 2 to the negative 4x plus 2. Now you can set those equal. All right, so let's see what we get there. 3x plus 15 equals negative 4x plus 2. Add 4x over here, subtract 15. Divide by 7, x equals negative 13 over 7. That one would obviously be a little bit harder to check, but it would check. That is the correct answer. You can check it graphically if you use your calculator as well. Now we get to the calculator active portion of the review and our modeling questions. Question 13. When investing $15,000 for 4 years at 7.5%, what is the yield when interest is compounded quarterly? First of all, that's a new word for us in this unit. Yield, that means interest earned. And we're going to apply our compound interest formula. A equals the initial amount, $15,000, times 1 plus the interest rate, so 0.075, divided by however many times we compound. So quarterly, n equals 4. To the 4 times the number of years, which is also 4. All right, so we'll just throw that into our calculator. I got $20,191.71. So our yield would be that amount minus our investment, our initial amount. So the yield ends up being $5,191.71. Question 14. If $12,200 is invested for 15 years, find the maximum and minimum values of the investment if the annual interest rate is 6.25%. We talked about this concept when we talked about compound interest. The minimum would be compounded once a year. The maximum is compounded continuously. So we're going to use two models. The first one I'll do is the simple, we'll call it the minimum, compounded once a year. A equals the initial amount times 1 plus r, so 1.0625 to the t, however many years, 15. Okay, so you throw that into the calculator and you get $30,289.63. Now the max is going to be our PERT formula. A equals the initial amount, 12,200, times E to the RT, so 0.0625. You don't add 1 to it, it's just R by itself, and times 15. Okay, so if you throw that into the calculator, we get $31,153.79. So just a reminder, max is PERT, compounded continuously. Minimum would be compounded one time. 15, a radioactive isotope has a half-life of 80 years. If there are 200 grams of the substance present now, how much the nearest hundredth of the substance will remain after 50 years? So our half-life formula looks something like this. A equals our initial amount times 1/2 to the T over K, where K is the half-life of the element. So in this particular model, we'll say something like A equals our initial amount, 200 grams, times 1/2 to the T over K. So the half-life is 80, that goes in the denominator, and T is 350 years. That'll go in the numerator. We'll throw that into the calculator. It says to the nearest hundredth, and I got 9.64 grams, which hopefully makes sense, because remember, you just want to estimate it quickly. You start with 200 grams, half-life is 80. Well, after 350 years, there's a lot more than just one half-life. So you take half, and then half, and then half. So you do that a bunch of times, yeah, you're going to end up with a number that's way below 200. Now the follow-up here. What is the percent decrease per year to the nearest thousandth? So for percent decrease, you want to make sure your exponential function is in this form. Well, how do I get that in that form? A is 200, so that's easy. But the variable needs to be by itself in the exponent. That is our t. That's this. So b in this case is going to be 1/2 to the 1 over 80. All right, so let me write that out. B is going to be 1/2 to the 1 over 80. If I calculate that, I get 0.991373. So that's going to be the B term. To get your percent increase or decrease, remember, it's how far this is from 1. So next, subtract that from 1. 1 minus 0.991373 equals 0.008627. And then we need to convert it to a decimal, which means move this over 2 places. So 0.1000th, 0.863. 0.863% decrease per year. Okay, next page. Given the growth model, P of t equals 5 times e to the 0.075t, where t is time in years and P of t is sales in thousands. What is the original number of sales? Our initial amount is 5 in thousands, so I would say 5,000. All right, it's just your A term. What is the number of sales to the nearest unit after 10 years? So just make sure this unit of time matches that unit of time. I just plug a 10 in there. Okay, so P of 10 equals 5 times e to the 0.075 times 10. And let's see what I get for that one. To the nearest unit, I got 10,585. What is the percent increase or decrease per year? So again, just make sure per year, that's great. So what I need to do now, remember, is get this y equals ab to the x. A is 5. Your b is going to be this right here, because then we just have the t on the outside. So your b term is e to the 0.075. And for that, I got 1.077884. And then remember, what you do is subtract 1 from that. So obviously that's 0.077884. Percent increase to the nearest tenth. So 127.8% increase. Now, this question is a little bit challenging. It says a pool contains 1,500 gallons of water. After 10 hours, 150 gallons has leaked out. What is the percent rate of change per hour to the nearest hundredth? So they want a model, percent rate of change. All right, they want a model for this situation. And what do we know? We know the initial amount, right? The initial amount is 1,500. Here's a data point. T equals 10. 150 gallons has leaked out. So you have to do a little math here. First thing, let's take 1,500 minus 150. So that's 1,350. At t equals 10, there's 1,350 left. I'm going to use my y equals ab to the x model. So what was the end amount? 1,350 equals the initial amount, 1,500, times b, which I don't know, to the t, which is 10. So here's what this is saying. After 10 hours, there was 1,350 gallons, and I started with 1,500. So now I just need to solve this. Divide both sides by 1,500. All right, that ends up being 0.9 equals b to the 10th. To solve that for b, you take both sides to the 1/10th power. So b equals, I got 0.989519. I don't need to write the whole function, all right? Just understand that it's this, and b is that value right there. All I need is the percent rate of change. So the percent rate of change is how far is your b term from 1. So now we're just going to take 1 minus 0.989519, and for that I got 0.01048. Convert that to a percent, move this over 2 places, and round to nearest hundred. So 1.05. 1.05% decrease, right? You have to mention decrease there. All right, last question on this page. Rank the following 3 savings account options from highest to lowest effective rate. Provide evidence to support your ranking. So we've got 5% compounded daily, 5.1% compounded monthly, 5.05% compounded continuously. So we have 2 formulas we're going to use here. Here's the first one. A equals P times 1 plus R over N to the NT. Basically, this part of that formula is the B value, right? In AB to the X. So all I need to do for these is calculate that portion of it. The initial amount doesn't matter. So let's do this, bank A. Your B term equals 1 plus the rate, 0.05, divided by however many times it's compounded, daily, 365, to the 365. Okay, so what is that B term? I got 1.05127. Okay, B, same formula. B equals 1 plus, this rate is 0.051 divided by compounded monthly, 12 to the 12th. Okay, so for that one, I got 1.05116. Now the last one, compounded continuously, we're using this. A equals PE to the RT. Well, the B value there is going to be E to the R, right? That's how you get AB to the T. So here, I need to do E to the R. So my B term will be E, and that's 5.05%, so 0.0505. That B value, I got 1.05108. So now we just need to rank these. All right, how do these rank? So it says highest to lowest. Which one of these numbers is the biggest? That one. There's first. This one's second. And that one is third. So this goes C, A, B. And this is plenty of evidence to support that. Question 19 is a different type of question than we've seen in this unit. It says, the following functions give an insect population as a function of time, t in months. Write a sentence that describes each population of insects. So A, what's going on here? That's not even an exponential function, but let's describe it. Initial population would be when t equals 0. So if t equals 0, this is 0, and the initial population is 28,000. All right, so what's happening to this initial population? It's decreasing by this much every month. So a sentence for this would be an initial population of 28,000 decreasing by 1,500 per month. All right, B. This is our classic AB to the T. Remember what A is, initial population, so that's easy, 450. This represents our growth factor. What are we increasing by? We're increasing by 5% per month. So this would be an initial population of 450 increasing by 5% per month. And then our last one. C is a little bit tricky. P equals 900 times e to the negative 0.03 t in thousands. So your initial amount is going to be 900,000. The next thing we need to do here is we need to find out what that b term is. So we need to evaluate e to the negative 0.03. So let's do that. E to the negative 0.03 equals what I get for that 0.970446. Then we have to subtract that from 1. All right, so 1 minus 0.970446 is 0.02955. And move it over 2 places, the decimal, 2.96. So this represents 2.96% decrease. Okay, now that I know the percent decrease, I can write my sentence. An initial population of 900,000, okay, decreasing by 2.96% per month. Okay, question 20. Another one's a little bit different. It says the temperature of a cup of coffee in degrees Fahrenheit T minutes after it is poured can be modeled by the function C of T equals 112 times e to the negative 0.13 T plus 72. So we're talking about the temperature of a hot cup of coffee. What is the horizontal asymptote of C of T? Explain whether or not this asymptote is realistic in this context. So there's a few ways you can approach this. Remember, we are now in the calculator active portion. So one thing you might want to do is put this into y1 and see what that looks like. Those of you that are really good with graphing understand that this is a negative exponential function. So this negative here reflects it in the y-axis. So instead of looking like this, it's going to look like that. And every exponential has a horizontal asymptote. You might also recognize this is shifted up 72. All right, so a quick sketch of this would look something like this. We would have a horizontal asymptote, and that would be at 72, right? Our vertical shift. And we have an initial temperature. What is the initial temperature? Well, the initial temperature is when T equals 0. So if T equals 0, I mean, you can get this on your calculator table as well, but if that's a 0, this is 1, and our initial temperature is 112 plus 72. All right, you have to take that into account. So this initial temperature right here is 184. So what is the horizontal asymptote of C of T? Well, the horizontal asymptote is y, or C of T, equals 72. Explain whether or not this asymptote is realistic in this context. Well, this is more of a physics question. If you think about what happens to a cup of coffee, you put it on the counter. All right, initially it's 184 degrees. The room temperature is 72. It cools in this negative exponential function. Well, an asymptote in the pure mathematical sense is a line that this approaches but never reaches. Well, if you think about it, you put your coffee on the counter and you come back the next day, it's going to be room temperature. It's going to get there. So the pure mathematical model is not realistic. And I would say something like this is not realistic because the cup of coffee will eventually reach 72 degrees. And then B, calculate the percent change per minute. So let's just make sure we don't have to manipulate the exponent. Minute, minute. Great, so I'm going to use this. So in order to use percent, or find percent change, I should say, remember, we need it to be y equals ab to the x. We need to find this b value. Well, in our function up here, the b value is going to be this. Here's a, here's b, there's t, and then we just have a vertical shift. So I need to calculate e to the negative 0.13. So b value equals e to the negative 0.13. And that is 0.1219046. So now what I need to do, that's not right. B equals e to the negative 0.13. And if I put that in the calculator, I get 0.878095. Then we need to subtract that from 1. 1 minus 0.878095 equals 0.1219046. Convert that to a decimal, move that over 2 places. All right, and it says round to nearest hundredth, so it's going to be 12.19. 12.19% decrease. All right, last question. Domino's Pizza experienced explosive growth through the 1990s. The 200th store opened at the beginning of 1991. T equals 0, so that's when we're starting this. By the beginning of 1999, there were approximately 2,500 stores. Approximate the annual percent increase between 1991 and 1999. So you can pick and choose your models here. You could use a PERT model, or you could use AB to the X. I'm going to use AB to the X because if we have to work backwards from PERT, we have to use natural logs, which we haven't reviewed yet. So I'll just model it like this. A of t equals AB to the t. All right, so what do we know? Initial amount, t equals 0, 200 stores. All right, so that's our A. Data points, beginning of 1999, so that means t equals 8. Right, 99 minus 91, there were 2,500. So that'll be our A of t. Plug those numbers in. 2,500 equals our initial, 200, times b to the 8th. Divide by 200, I got 12.5 equals b to the 8th. To solve this, we are going to take both sides to the 1/8 power. So b equals, what I get for that, 1.37124. So the question says approximate the annual percent increase. So there's my b term. I subtract 1 from that. So 1.37124 minus 1 is 0.37124. Move your decimal over 2 places, 1, 2. It says round to the nearest, doesn't say what to round to. Let's go 10th, 37.1. So that's going to be a 37.1% increase. Assuming the percent growth remains constant within this time frame, create a function d equals p of t that models this data. A regression model is not acceptable. Don't worry about a regression model. So d equals p of t equals our initial amount, 200, times our b value, 1.37124, to the t. That's all we had to do. And then lastly, it says, give a mathematical explanation for why this trend is unlikely to continue over a long period of time. Well, think about what this looks like. We start at 200. We have exponential growth. That's positive. So graphically, it's going to look like this. There's 200, and it's just going to do that. So what is this end behavior? As x approaches infinity, y approaches infinity. So is it possible to have an infinite number of dominoes? I hope not. So let's just explain that. The end behavior of this function is as x approaches infinity, y approaches infinity. And then something like it is physically impossible to build that many Domino's pizza joints. Okay, so that finally concludes this video key of the review. If you guys have any questions, don't hesitate to reach out. Thanks for watching, and good luck on the exam.